talk is from Martin Strauss, and we're continuing on what has been a fantastic session this today. So please.
Well, thank you. I'd like to thank the organizers as well. I'm going to talk about joint work with my co-author Ellie Porat, and also some work in progress with Ellie and other co-authors Anna Gilbert Yi Lee coming up. So the sparse recovery problem that we've seen many times already, again, change the notation perhaps. We have a signal X, which will measure by a linear process. There is some noise added, potentially. For today, you can pretty much ignore that. And then we want to recover some approximation to X by potentially nonlinear process. Some of the criteria that we're interested in for algorithms are, first of all, speed. So this is Mark Cavendish won the Tour de France sprinters competition a few days ago. Accuracy, and of course, the number of measurements. Actually, so this is an homage. This cup of P is an homage to the original group testing that was done to detect various diseases and irregularities from specimens. So anyway, the number of measurements that we're interested in for our algorithms is k log n over k, which we'll see coming up again, which is basically the log of the number of configurations of k places among n, if you have a k-sparse signal of ambient dimension n. Okay, the recovery time we really want is sublinear, in my view as a computer scientist. It's a polynomial time in the sparsity k, about the size of the output, and logarithmic in n. And then you can quibble about whether it's k squared or k and so on. But the idea is, in many cases, you don't want to have to go through the ambient dimension to do the recovery process. Okay, I also want to say something about these sublinear time algorithms. We're going to be comparing our time to other algorithms that use the optimal number, k log n over k, of measurements. A traditional algorithm would take n measurements, maybe run in time n, maybe n log n for a fast Fourier transform. And superlinear fast Fourier transform is going to beat our sublinear algorithms every time, except for very unusual values of k, you know, all the overhead and so on. But other measurement optimal algorithms actually are much, much slower than fast Fourier transform in cases. And that's what we want to beat by proposing a sublinear time algorithm. Okay, accuracy, the picture is a bit more complicated, unfortunately. We'll try to focus just on the model for today. We want to recover all signals by one matrix. The signals are geometrically constrained, as Anna Gilbert talked about a while back. In the smaller L1 ball, smaller than the L2 ball, it's constrained. So smaller than you might otherwise like, but this is actually tight for this model. Okay, this is the model we're in. There are other models. Okay, we're also interested in the norm of the error of our of what we return. Ideally, we'd want to bound the error of what we return, x hat, away from the true signal x in 2 norm. Instead, and this is probably strictly worse, we'll only give a guarantee in 1 norm. Okay, after it's normalized properly, this is strictly worse than that, but it's a step in the right direction. Okay, so here we have a matrix sparsification of the general matrix that's put up at this stage in the talk in theoretical computer science. So just a few results. I'm sorry if I'm missing people, but trying to keep focused on today's topic. So in 2007, Gilbert, Strauss, Tropf, and Verschinen showed that you can get sublinear time, polynomial in k log n, less than n, but the number of measurements was suboptimal. And the norm in which we measure the error was optimal, the 2 norm, what we like. Okay? Earlier than that, there's a long history in this that I'm omitting, but in 2004, Donahoe, Condes, Romberg, Tau gave the right number of measurements. The runtime, however, was much greater than n. At least theoretically, you're doing a linear program of size about n, and that's very expensive. Okay, and these things have been improved in many different directions by different folks. I want to mention in particular Ruzic and Indyk that got the right number of measurements and improved the runtime to just barely superlinear. N log n at most, closer to n in many cases, although the norm was still suboptimal. And today what we're going to do is get both the number of measurements and the runtime essentially optimal up to whatever you mean by essentially. The norm is still not what we would desire, but as I said, a step in the right direction. Okay, I just want to mention quickly, I can't go into the subtleties about how the different models are incomparable or not, but there's some other folks in this room elsewhere that have worked on problems and have gotten runtimes that are very good, just barely superlinear. Again, depending on the model, which I won't get into. Okay, so here's a technique that often comes up in these sublinear time algorithms from group testing. We use this matrix, the Hamming matrix, has a long history over Z2. We'll use this over the reals. Okay, so under the top row of all ones, we have all the columns of length 3, zeros and ones. And if we apply this to a matrix, to a vector signal with is one large entry, the rest noise, think of, in the second position, what we get is a measurement vector that looks like this. This top row sort of gives us a reference that picks out the big guy, and the noise adds up, doesn't make that much difference. You can prove that. And once you have the reference to compare things to, you can say that whatever you get here for this measurement, you add up these 4 noises, it's going to be small compared to the reference because it omits 7, whereas this measurement includes the 7 plus some noise, so it's going to be approximately 7. So you get to read this 070, divide by the reference, get 010, which is the index of the column in binary, the second column, 0, 1, 2, 3, and so on. So from this measurement vector that you get, you pretty much can read off the index of the one heavy hitter in the signal, if it's one sparse. And the number of measurements for this is logarithmic in n. Okay, so how this is applied in general when you have a k-sparse signal, a k bigger than 1, is often as follows. So we'll take a matrix to hash the signal into buckets. That means, in this case, 2 buckets, and we'll assign each of the n equals 8 positions into 1 or 2 of the buckets. So, for example, position 0 goes into this bucket, 1 goes into this bucket, this one's missed, 3 goes into this bottom bucket here, and so on. Okay, now we have this matrix from before, and we combine it with this and multiply together the number of rows. So, for example, the top row of this hashing matrix picks out columns where you're going to do anything at all. And what you do there is you take a copy of this matrix. So you have a copy of this matrix masked by each of these rows. And typically, the number of rows in H itself already uses up your budget of k log n over k. And you can solve the problem sublinear by taking the extra log factor of rows to do this. Okay, the idea is when you hash into k log n over k buckets, more or less, you're likely to get a lot of buckets with just one heavy hitter, one important item, and then you can apply the fast sublinear time technology for finding that one guy. Okay, but we want to avoid that log factor. Okay, and so let me present the algorithm sort of in summary and then talk about it a little bit. What we're going to do is the following. You choose some number b. In general, it's a parameter. Think of it as square root kn for now. take the original signal, hash into B buckets. Okay, and then aggregate. So we have a bunch of original positions that all end up in the same bucket, just sum up their values. What we get from that, we start with a k-sparse signal of length n, and it turns out we're likely to get it almost k-sparse signal, maybe k over 2, we lose a little, signal of length b, the number of buckets. Okay, we measure that signal using some optimal algorithm, k log b over k measurements. We repeat this whole process a second time. The actual number of b as a parameter is log n over k over log b over k. And I'll show you a little bit where that comes from in a second. And we collect all those measurements. Okay, so you have to believe me that you can do this whole process by the matrix vector multiplication process. It's not difficult, but it's sort of cumbersome to explain all this. But I showed you hashing and collecting is all things you can do with matrices. Okay, so what do you do next to recover? Well, we have a recursive problem, 2 instances actually. We use the recursive solution here, okay? And we can do this naively. So we have measurements, the measurement vector of length k log b over k. We're trying to find the k heavy hitters in a signal of length b. The time, if you use a good algorithm, is roughly the length. A little bit more than the length, that's okay. B is quite a bit less than n. Okay, so the time is about b squared kn to recover heavy hitters here. And then we want to lift the solution. Okay? And from table means we're just storing a table of back pointers. Okay, if you remember, originally we hashed from the original positions, just use a random assignment from length n to length b. It's generally hard to invert this. We'll just store the inverses in a big table. Uses a lot of space, but it's very quick and straightforward. Okay, the time to do this, when we can invert quickly like that, is basically the number of possible pre-images. Okay, so what happens? Here in the signal of length b, we have about k heavy hitters that we've found. Each of these buckets is mapping from n into b. There are n over b items, n over b pre-images of each of these heavy hitters at this level. That's k times n over b altogether. Square root kn if you balance things, which is the best thing to do here. So the total time is about square root kn for the recursive problem and for the lifting. That's pretty much what's going on here. Okay, good. Okay, so a formal result, the algorithm takes time about square root kn, uses about k log n over k measurements. What we have to do to show this is the number of measurements, runtime is correct. I just showed you that more or less. Correctness of the hashing procedure, that'll go into a little bit of detail. Hope to show you why we need 2 repetitions, no more, no less, effectively, and why we actually get a k-sparse signal of length b, approximately k-sparse. Correctness of the recursive solution, well, we're using pre-existing literature, nothing to do there. And correctness of the lifting, correctness of the lifting, we use this table. So we're not doing anything exciting there either, but in upcoming work we will be. And I hope to get a chance to talk about that as well. Okay, so correctness of the hashing. We're taking a signal of length n, we're assigning each position to one of b buckets, and then we're summing all the values. So all the positions that get mapped to this bucket, they have values associated with them. Sum them all up, that's the value associated with this bucket. The buckets index the intermediate signal. Okay, so why is that a good thing to do? Each of the important items in the original signal is isolated except with probability k over b. You can go into one of those b spots, and at most k of them are already occupied by some other heavy hitter, and then it fails, otherwise it's good. And these are more or less independent, and so if you want to ask, will, say, half of them survive this process, the failure probability is exponentially small in that number, k over 2 about. So the failure probability goes down to about k over b to the k, 2 to the negative k log b over k. On the other hand, a heavy hitter landing in its bucket could be clobbered by a lot of noise. And I'm leaving out a lot of details and cases, but a canonical case here is as follows. You have some set S where the heavy hitters land that you want to preserve, and you want to know that in aggregate the noise doesn't clobber that too much. If you have T noise items of size 1 over T, normalized this way, the noise items are smaller than the heavy hitters. Those K heavy hitters occupy a set S of size about K. The noise items land there with probability about K over B. And you get most of them, or half of them, with probability exponentially small in T. So again, 2 to the negative T log B over K. These numbers are just a little bit too big in failure probability for what we need. If we repeat log n over K over log B over K times, then we get the right failure probability. Lowers to 2 to the negative K log n over K for this one. T, you have to do some more analysis. T is always bigger than K, 1 over T, less than 1 over K. The noise items are smaller than the heavy hitters. But that's what's basically going on. The failure probability drops to 1 over this binomial, and you can take a union bound over the configurations, basically, and over the noise configurations as well, and you're done. Okay, more generally, I don't want to go through this unreadable slide too much, but what I showed you was a two-stage thing. We'll hash into B buckets, solve recursively, then lift. We can have a sequence of L levels, any integer L that you choose, and if you do this in a straightforward way, the runtime drops from this geometric mean, square root kn, to a weighted geometric mean, say k to the 3/4 n to the 1/4, which is equivalent to saying k times n over k to the 1/4. So you can get that runtime closer to k if you like, but you choose L, you pay a little factor in L here, and a little factor of L in the number of measurements. So L has to be a constant to keep this honest, and you never really escape down to k times logarithmic in n for the runtime. You would need L to be logarithmic for that, extra log factor in the measurements. Okay, but we're not limited to just square root kn. We can do a little bit better. Okay, let's see what we can go through here. Next results, improvement on this in process with Anna Gilbert and Yi Li, as well as Ellie. What we want to do is first avoid this lookup table for inverting the hash. It's one thing. And we want faster runtime from this geometric mean in k and n down to polynomial in k and log n. So here's the idea. When we recover a heavy hitter I recursively, it turns out we can also get an arbitrary log b over k message. Heavy hitter I from a k-sparse signal of length b. Okay, and we're going to use that message to code up back pointers so we don't have to look up in the lookup table. Okay, we can sometimes code the whole back pointer, sometimes not. That's one of the crucial issues. Okay, we don't have to store the pointer explicitly, only need to run the hash function forwards, which is easier than running it backwards. Okay, here's the way this works. So we're turning the error correction problem a little bit on its head for this. We have these messages that we want to encode to recover at the right stage to help us point back to identify where the heavy hitters are. There's an encoder and decoder. They're agreeing on some measurement matrix phi. The encoder gets this message vector m of these back pointers. Oops. Okay, reserve battery level. My clock will run out soon. Okay, so this is message m of length b, alphabet size b over k. Those are the log b over k bits we want to encode up. The encoder takes that message and the measurement matrix it's agreed upon and produces a new measurement matrix phi prime, encoding m into phi prime. Now this is what the channel does. The channel operates on phi prime, the code word phi prime, by applying it to the signal x, what we were calling the signal x, and adding the noise optionally. okay, and produces this measurement vector. Now, it's a decoder's job to recover the original vector M of messages, okay? But in this weighted sense, the decoder only needs to recover the messages. There's one for each of the B positions, but only needs to recover the messages in case the ith position of X is big. It only needs the messages to recover the heavy hitters. Otherwise, it doesn't, and there's no hope. There's way too much information to recover all of it. Okay, so how do we do this? Running a little short on time. It's similar to the combination I showed before with group testing, except we're not going to try to code up log n bits in a naive way. We'll only code in one bit at a time. And if the original hashing matrix is k log b over k measurements, we can actually code log b over k bits, and with error correcting codes, we can get that reliably. Okay, so what this means is we get a heavy hitter recursively. We can get any log b over k bits of our choosing that we've coded in there that can help us to recover the original heavy hitters when we do the lifting problem. Okay, now if log b over k is about log n, we're done. We only need log n bits to code a pointer, back pointer. Right. But sometimes there are more complicated situations. I just want to go over what those issues are. We call the algorithm, we're hashing into B buckets, repeating R times, R was 2 previously, solve recursively, and our goal is to come up with log n bits of a back pointer that'll tell us how to lift the solution. In the jth repetition, up to R equals 2, or maybe up to log n, whatever, we get a few things. So we get log b over k codable bits, whatever bits we wanted. We know what j is in the jth repetition. And when we recovered a heavy hitter in the jth repetition, that's some index ij into a signal of length b, we know what that is. And it turns out that for various values of k, none of these alone suffices. You have to carefully code more than payload, but actually some linking structural information to mi, and use this j as well as the ij and put it all together and try to do this in sublinear time in order to succeed. Okay, and I think I have a few minutes. Just give a teaser of how this goes. If you're asleep, now is a possible time to wake up. Something of side interest in network coding. Also, please correct me if I'm wrong about some of these assumptions. I'm not an expert in this. So what is network coding, which is a side problem that we need for our problem here? Suppose you have a message, think of a movie, length n, and you want to download it for later viewing, which is a particular model. We're not streaming it. We're not getting a DVD by mail. Oh. Is there a... Is this off? That's off. I have my laptop.
You guys don't have the power strip plugged in? Could you help us find the outlet for it?
Can I do this in the meantime?
Got the, but I don't have anything to connect it to.
I'll fold this in the meantime here and let me continue.
Sorry about this.
No problem. Okay, so we have a message of length n. Think of a movie that we're going to download now for later viewing. We have a flaky network. So in the olden days anyway, it would take 3 hours to download a 2-hour movie, and the network would drop every 15 minutes or so. So you get erasures for now, but no errors. How can you proceed? Okay, so the goal of network coding is a publisher breaks the message of length n into p packets encodes them somehow, and just keeps broadcasting packets. And what the subscriber needs to do is to collect any P, maybe 2P, 5% more than P packets, and somehow can rearrange them and get the movie. Okay, and there are protocols for this. Okay, just as an example, and there are more details, but the publisher could just keep sending new points on the graph of some degree P polynomial, and the subscriber collects P plus one of them. They can reconstruct the polynomial. It doesn't matter which points. Okay, and they're all different. Okay, so the multiple stream network coding problem is as follows. You have K messages all at once, let's say the same length, and they're transmitted simultaneously. They're interleaved arbitrarily. The total is Kn bits. And we want to make the requirement on the receiver to recover just any total Kn bits in packets without having to label each packet as to which movie it's from. Okay, that would be an extra log K bits per packet, not just once. Okay, that log K would break our problem altogether. We're trying to avoid an extra log factor. And it would also avoid giving constant rate to this whole procedure in general. Okay, so we think we can solve this, and we think that this is new, but I'm glad to hear from other people about this. And I can't go into details today, and the paper isn't written yet, but anyway, that's that. I also want to mention that we get error correction for free from this kind of procedure because simulations have verified this. It turns out that the packets from one movie can be regarded as noise in another movie. So if you can recover the color purple even when you're getting Dumb and Dumber at the same time, you can recover it even if you're getting other noise and so on. Okay, so to summarize what's going on, the algorithm runs in time. It's maybe polynomial in K. The paper's not quite written yet anyway. But polynomial in K log n using the optimal number of measurements and returns a near optimal approximation in one norm. Okay, and improving this to two norm would finally bury this problem in terms of speed, accuracy, number of measurements, which I think would be a good thing. So that's no, it's okay. It's all right. You can't fall off the floor. Yeah, you add new. Yeah. The question is, what happens if you also have measurement noise? In other words, the recoverer gets not phi x, but phi x plus nu. Okay, and so the short answer is some amount of measurement noise will be handled. I optimistically think the right amount will be. The paper isn't written yet for the next result, but I think that will work.
And the second quick question. So it shows the algorithm recovers the heavy hitter. So it means that it also recovers the support, right? Or
yeah, I mean, the question is whether when you recover the heavy hitters, do you get the support? We're trying to, the way it's phrased is we're trying to recover a representation of the original vector, which includes getting the support and the magnitudes and the phases right, or close, for most of the heavy hitters. And I left out details that are handled in previous work. It suffices to get half of them, then you can iterate, and there are things of that sort. But yes, you have to get the supports, magnitudes, and phases in general, complex. So I didn't catch all the question, but it's about, I'm sorry? It's about getting the L2 to L2 error. That you cannot do if you want one matrix to work simultaneously on all signals. Okay, so there's a lower bound due to, I forgot, Piotr mentioned it earlier. That's another model where you can also ask for sublinear time recovery, optimal number of measurements, and that was done by my co-authors and me last year. But it's an incomparable model. You can't hope to get L2 to L2 with a single matrix for everything. Okay?
I think we're going to, well, thank our speaker again.